Okay, let's start talking about triple integrals in spherical coordinates. Okay, the first thing I'm going to put up here is a little drawing here that will help us understand the correct volume element. Okay, so this will be essentially finding the dv that you're going to need to use spherical coordinates. Okay, all right, let's go over here, and I will be posting this picture online along with a more formal explanation. Okay. But let's get the basic idea here from the drawing. Okay, I've got a part of a sphere here, and I hope you remember phi, rho, and theta, what those mean, right? Okay, let's go ahead and see this. I've got a little wedge here, and I'm going to approximate it as a Cartesian wedge, even though parts of it have a little bit of curve on it, okay? The first change I'll think about is in the direction of the directly from the origin. So that would be what? A change in rho. So that's d rho. Okay. Probably the next easy one to see here is the following. The dimension here on this Cartesian-like wedge here, even though that has a slight curve to it, right? You remember from basic trigonometry that arc length is what? S equals the radius, right? Times the change in angle, okay, or the angle there that you're measuring, okay. Of course, that's got to be in radians for that nice formula to hold. Well, if the radius on this is what? Rho, and then you think along here, you've only got a change in phi, so that that length is actually rho d phi right here. So that's this dimension here, okay. And then we've got a dimension here. There's one last dimension here. We want to change here in the theta, okay, direction here. Let's go back and remember that r is rho times the sine of phi, right? Okay, so r is rho sine phi. So think of that as the polar r, okay? And then I'm making a change in what? Theta. So we think about this formula again, the change in this direction here. So this length here would be what? R d theta, which would be rho sine phi d theta. And now, because this is a Cartesian wedge here, I'm going to multiply these quantities I have circled in here together. And we're going to have dv is what? 2 rho's here, so that's rho squared, and then the sine of phi, then d rho d phi d theta. Okay, so you're always going to have to include this little volume element here for your dv. It's okay to write dv in the beginning, but if you're using spherical coordinates, ultimately you're going to have to go rho squared sine phi, and then d rho d phi d theta in some order, and this is pretty much the typical order for most of our problems. So rho first, phi next, and then theta at the end. What are spherical coordinates good on? They're good for what? Figures that have, yes, origin symmetry. Okay, let's look at some concrete problems now. Let's look at our first example. Find the mass of the solid that lies between the concentric spheres of radii 1 and 3, centered at the origin. Well, they're with their centers at the origin, if the density of the solid is proportional to the distance from the origin. Okay, so density is going to be proportional to distance from the origin. Okay, now that means differential mass, let's say m is mass, is going to be that density function times differential volume. Okay. Now, since we're going to be using spherical coordinates, the density function will be some constant multiple of what? The distance from the origin, which we're calling rho. And then dv is what? Rho squared sine phi. Okay? d rho d phi d theta. Okay? So our integral is going to be looking like this. K, whatever that is, we didn't say what the constant of proportionality is here, but that's going to be what? Rho cubed then, sine phi d rho, d phi, d theta. Okay, let's go ahead and make a statement. Mass is equal to, now we have to set up the limits of our integration here. And since we're dealing with spheres here, you can imagine the limits of integration are going to be really easy on this particular problem. And they are. Okay, let's get our integrand in there first before we do anything else, though. Okay, now if I fix theta and phi here, and just consider what's happening to rho, where would rho be going from and to? Well, it would be going from what? Any edge or any point on the smaller sphere straight out to what? Corresponding point on the larger sphere. So rho would be going from 1 always to 3. Okay? How about phi? Remember, phi is measured from the positive z-axis. That would always, regardless of theta, that would be always going from what? 0 to pi. Okay? That means straight up to straight down. Okay? And then we'd be going all the way around, so theta would be going from 0 to pi over 2. So you notice on this problem, we've got what? Nice constant limits of integration, which is probably what you'd expect on such a perfect problem, right, for spherical coordinates. Okay? So there it is. Let's go ahead and work this now. Let's do the innermost integral. We'd be integrating from 1 to 3, constant rho cubed d rho. Okay, I could actually take the k out here. But I'm really interested in taking out what? The sine of theta is going to be independent of rho here on such a simple problem here because I've got constant limits there. So this is going to be what? K over 4 rho to the 4th power going from 1 to 3. Okay, and what is that going to be? That's going to be 3 to the 4th. That's what, 81? Is that right? Yeah, minus 1 to the 4th, which is 1. So that's going to be 80 divided by 4 is 20. So we've got 20k. And then we're going to be doing what? We're going to be going from 0 to pi. 20k sine phi d phi. Okay. Now the integral of the sine of phi with respect to phi is what? Negative cosine of phi. And phi is going from 0 to pi. So you can see that's going to be negative 20 times, let's see, the cosine of pi is negative 1. Okay? The cosine of 0 is 1, so I'm subtracting 1. That gives me negative 2. So I've really got what? 40k. Okay? And then finally, to get my mass, I didn't give you measurements. Maybe it's grams or kilograms or something. Anyway, 0 to 2 pi, 40k d theta. And you can see that's 40k times theta, going from 0 to 2 pi. And you can see that in your head that that's going to be what? 80k pi in whatever measurements, kilograms or whatever. Okay, so this one turned out to be pretty simple here, okay, which we would expect from the geometry involved. Fortunately, the integrand was pretty simple, okay, pretty easy density function there. Okay, let's take a look at a second example. Find the volume of the solid ice cream cone that lies inside the sphere centered at the origin that has what? Radius A that lies above the cone phi equals some fixed alpha. Okay, so A and alpha are fixed. If you remember in a previous video, we did this using cylindrical coordinates. Let me show you, as you could probably guess here from this shape, that it's actually easier to do using spherical coordinates. Okay, so let's go ahead and set up our triple integral here. Okay. Now, since I'm just looking for volume, my integrand's going to be dv, right? dv. Do you remember that's what? Rho squared sine phi. And then what? d rho, d phi, d theta. Is our typical order here. All right. Now, if I fix phi and theta, rho would always be going from what? The center, so the origin, I should say, out to the edge of the cone. That would go to what? Rho equals 0 out to that fixed A. Right? All right. Okay. What about phi? Where's phi going from and to? Well, it's independent of theta. Phi is always going from 0, straight up and down, right? The positive z-axis, out to what? Alpha. And then where's theta going? Actually, I think in all my examples, theta is going all the way around, so 0 to 2 pi. So this would be the appropriate integral to find the volume of that quote-unquote ice cream cone. Okay, so let's go ahead and work out this integral and compare it to the answer we got with cylindrical coordinates. Okay, now the innermost integral, you're going from 0 to A. Okay, rho squared d rho. Notice that once again I have no dependence with my limits of integration here on the integrand or phi, so I'm just going to integrate this. And what do we get? We get 1/3 rho cubed going from 0 to A. So that would be, you can do that in your head, that's 1/3 A cubed, isn't it? Okay. And then for the second integral, we'd be going from 0 to alpha, 1/3 A cubed. Okay. I could put this outside everything since A is a constant, but I guess I'll leave it. Okay. And then what? Integrating sine phi, d phi. Okay. The integral of the sine of phi again is what? Negative cosine. So we get negative 1/3 A cubed cosine phi. And that's going from 0 to alpha. So we would get negative 1/3 A cubed cosine of alpha minus cosine of 0. Cosine of 0 is 1. Okay, so let's go ahead and apply that negative sign in there and just change the order of our differences. So that's 1 minus cosine alpha. Okay, and finally make a statement about our volume. We're integrating from 0 to 2 pi, 1/3 A cubed, 1 minus cosine alpha d theta. Now, again, these have no dependence whatsoever. These are constants, right? No dependence on theta. This is so easy. You can do this in your head. You can see that would just be what? Theta over 3 A cubed, 1 minus cosine alpha. Why theta goes from 0 to 2 pi. And you can see that would be what? 2/3 pi A cubed, 1 minus the cosine of alpha. And I'll put V and box in my final answer. If you go back and look at the previous video here, this is exactly the result we got using cylindrical coordinates. This was a little bit easier though, wasn't it? Okay. Okay, let's go ahead and try a related problem here. Find the mass of the flat-topped cone with density directly proportional to distance from the origin again. Okay, now here's the flat-top cone I'm imagining here. The top of the cone is the plane z equals 1. Okay, so that's parallel to the xy plane. And the edge of the cone itself here is phi equals pi over 3. It looks more like pi over 2, but nobody's perfect. Okay, so you see what I mean here? It's like our previous problem with the ice cream cone, only it's not what? It's not a spherical top. It's flat on top there. Now I'm wondering what the mass of this thing is. Okay, the previous problem was just volume. Here I'm interested in mass. Now differential mass then is going to be what? Proportionality constant times the distance from the origin, which is rho. So it's k rho times what? Differential volume. Okay, what is differential volume in spherical coordinates? Rho squared sine phi d rho d phi d theta. So putting these together, differential mass should look like this. K, whatever that is, rho cubed sine phi d rho d phi d theta. Okay? Now, when we're setting up our integration here, to find the limits of integration here, we're going to think about it this way. Okay, we're going to integrate with respect to rho first, right? Okay, where is rho going from and to? It's going from the origin, so rho equals 0, out to what? Some point on the plane z equals 1, right? Okay, so now you can tell here that that's going to depend upon the corresponding phi, right? Okay, it's not going to depend upon theta, but it is going to depend upon phi. So what I did was go ahead and make a little drawing here. If I take an arbitrary point there on the surface of that plane here, and imagine drawing a line, I wrote it as a dashed line here from the origin to that point, and then projecting that onto the positive z-axis here. Let's go ahead and take a look at this. You'd see I would call this angle phi from the positive z-axis. I'm saying the rho I'm looking at is the length here from the point to the origin. Okay? And if like I said, if I project that thing onto the positive z-axis, then you know this measurement's going to be 1, right? Because it lies on the plane z equals 1 here. So now I can get rho in terms of phi. Now, you remember in general that z in spherical coordinates has the property that z is rho times the cosine of phi, and I'm intersecting that with z equals 1, so I've really got, for points on that plane, 1 equals rho cosine of phi, and therefore rho is 1 over the cosine of phi, or rho is equal to the secant of phi. So this is going to be my upper bound on the rho here, when I'm integrating with respect to rho. But you could see that also in my little drawing strictly from the trigonometry, right? Okay? Yeah. The side adjacent, the hypotenuse gives you this. Okay? So you got that if you want the rho. So let's go ahead and do this. Let's set up our integral now and make a statement. Mass is going to be triple integral here. Okay. All right, we've got to get our integrand in there properly. Sine phi d rho d phi d theta. And we said what? Rho, first of all, is going from 0 out to that, right? The secant of phi. Okay. Now, where is phi going from and to? Okay, phi is always going from where? From 0 out to pi over 3. Okay, and then how about theta? Well, again, like usual, I'm going all the way around. If you were going halfway around or something, I would have just, at half of this thing. Then I'd go from 0 to pi, but I'm always going all the way around on these things, so it's 0 to 2 pi. Now let's work the inner integral here from 0 to the secant of theta, k rho cubed, d rho, okay? Just factoring out the sine of phi again, like usual. What do I get? K over 4 rho to the 4th, going from 0 to the secant. of phi. And you can see that's really going to be k over 4 secant to the 4th phi. Okay, so that's my innermost integral result. And then I need to integrate that with respect to phi, right? Don't forget your sine of phi in there. But you're going from 0 to pi over 3, k over 4 secant to the 4th phi sine phi d phi. Okay. Now, how are you going to work this one? Well, obviously, you can take the k over 4 out, but here's what I would think about doing. Do you see what to do? Okay, the secant to the 4th is really cosine to the negative 4th of phi, and then I've got sine phi d phi. So if I have a u substitution here, I would have u is what? Cosine of phi, and then du would be what? Minus sine phi d phi. Okay? So we could go ahead and do that very easily then here, or obtain the k over 4. Okay? So let's just imagine here, that would be cosine, add 1 to the power, and then what? Divide. Okay? Okay, do a quick mental double check here by differentiating. The negative 3 multiplies in front, canceling the 1/3, but I would have a negative sign, so I'd have negative cosine to the minus 4th, but the derivative of the cosine is what? Minus sine, so I would end up with what? A plus sign out there. Okay, so that looks just about like what I'm interested in doing here. Okay, and then we're going from what? 0 to pi over 3. Okay, what would that be? Oops, why don't we go? Well, okay, I guess I'll leave it. I've got a 1/3 there. Okay, what's the cosine of pi over 3? Do you remember? That's a half, isn't it? Okay, so I've really got 1 over, because it's the minus power, right? I've got a half cubed, and then minus at 0, that's over what? 1 cubed. Okay, so it looks like I get what? 7/12? Is that right? I get 8 minus 1 is 7, so I get 7/12 of k. And then finally for my mass, I'm integrating from 0 to 2 pi, that thing again, d theta, and it looks like I get 7/6 pi. Now let's write k pi. 7/6 k pi, I think. Okay? All right, I think we're looking good there.